Okay, in this lecture we're going to continue with our section 3.2 material on trigonometric integrals. Now in the first part of this lecture we had discussed techniques for integrating powers or products of powers of sine or cosine of x. So in this next part of our section we will be considering integrals of the following form. The integral of secant x to the nth power times tangent x to the mth power. So here we will be considering integrals of products of powers of secant or tangent of x. So as we had considered for integrals involving powers of sine or cosine, there are three cases which we will be considering here. The first case is if m is odd. So that is if the power of tangent is odd. Then we will factor out a secant x times tangent x, so that if I had an odd power of tangent, when I factor out something involving tangent to the first power, I will only have even powers of tangent. And I can make use of the identity tangent squared x is equal to secant squared x minus 1 to rewrite everything in terms of secant. Now, if once I have everything in terms of secants, I can make a u substitution where u is equal to secant x, in which case du is equal to secant x times tangent x dx. And here, since I had factored out a secant x tangent x, I can see that it's going to cancel nicely with this secant tangent x dx term that I obtained for the differential with du. Now, our next case is if n is even. That is, if the power of secant is even, then we're going to factor out a secant squared x. So if I had an even power of secant and I factor out a secant squared x, I'm only left with even powers of secant. And I'm going to make use of the identity that secant squared x is equal to 1 plus tangent squared x, in order to rewrite all of the even terms involving secant in terms of tangent. And then I will make use of the substitution u equals tangent x, so that du will be equal to secant squared x dx. And when I rewrite my integral in terms of u, this factor of secant squared x that I had pulled out from the integrand will cancel nicely with the secant squared x dx term that I had for the differential du. Now, the last case, which is the trickiest, is if m is even, so that is if the power of tangent is even, and the power n of secant x is odd, then we will use the identity tangent squared x is equal to secant squared x minus 1, and we will use integration by parts to evaluate all of the secant x to the nth power terms where n is odd. So if we had even powers of tangent and odd powers of secant, I can use tangent squared x in terms of secant x to rewrite everything involving even powers of tangent in terms of secant terms. And if the power of secant was odd, when I multiply that by this secant squared x to the first, or secant x squared minus 1, I'm left with only odd powers of secant. And we can then use integration by parts to evaluate those integrals of odd powers of secant. So let's look at some examples of these types of trig integrals, and we'll look at examples of each case here. So in our first example, we're asked to evaluate the integral of secant x cubed times tangent x cubed. So when we look at this one, we can see that the power of tangent x is odd. We have tangent x to the third power. So I can make use of the first case that we had discussed here. And since the power of tangent is odd, I'm going to factor out a secant x times tangent x. So if I had secant x times tangent x cubed, and I factor out 1 power of secant and tangent, then I would be left with secant squared x times tangent squared x. And then I've got my extra factor of secant x times tangent x on the end. Now, once I have factored out that secant x tangent x term, I'm going to make use of the identity tangent squared x is equal to secant squared x minus 1. So I can rewrite this as secant squared x times secant squared x minus 1, and I still have the secant x times tangent x dx on the end. So grouping all of my secant x terms together by distributing, I have a secant x to the fourth power minus secant x squared times secant x tangent x dx. And from here, I can make use of a substitution. U is equal to secant x, so that du is equal to secant x times tangent x dx. So this allows me to rewrite our integral in terms of u as the integral of u to the fourth minus u squared, and then this factor that I had on the end, secant x times tangent x dx, when we made our substitution, we found that that was exactly du. So I'm just left with the du on the end. And now once I have this polynomial expression in terms of u, I know how to integrate it. I would have a 1/5 u to the fifth minus 1/3 u cubed plus c. Or to get my final answer in terms of x, I'm going to take u, which was secant x, and substitute it into this answer, giving me 1/5 secant x to the fifth power minus 1/3 secant x cubed plus c. So this first example illustrating how to handle an odd power of tangent x. Now in part B, we have tangent squared x times secant x to the fourth. So we recognize it immediately as a trig integral. It's an integrand involving products, or a product of powers of secant and tangent x. So I have to decide which of these three cases I'm working with. And I see, first of all, that the power of tangent x is even. So I can't use the same approach that we had used in part A. So I then move to the power of secant x. Well, I see the power of secant x is even. So I could use the second case that we had discussed above, which said if the power of secant is even, I could factor out a secant squared x, which would leave me with tangent squared secant squared x. And then I've got my extra factor of secant squared x on the end. Now from here, I can make use of a substitution, or make use of the trig identity, that secant squared x is equal to 1 plus tangent squared x. So I'm going to try to rewrite everything in terms of tangent x, except for that last factor of secant squared x that I had peeled off. So if I group all of my tangent x terms by distributing, I would have the integral of tangent x squared plus tangent x to the 4th power times secant squared x dx. And from here I can make use of a substitution. I'm going to let u equal tangent x so that du is secant squared x dx. So then rewriting my integral in terms of u, I would have the integral of u squared plus u to the 4th, and our secant squared x dx, when we made the substitution, we found was just equal to du. So from here, we know how to integrate. We have a 1/3 u cubed plus 1/5 u to the 5th plus an arbitrary constant. Or, getting my final answer in terms of x, I would take u, which was tangent x, and substitute it into my answer. So I've got a 1/3 tangent x cubed plus 1/5 tangent x to the 5th power plus c. All right. So we've seen examples from our first couple of cases. So let's look at some other examples. In part C, we're looking at the integral of tangent x cubed times secant x to the 5th power. So here, let's see which case we're working with. We recognize it immediately as a trig integral involving powers of secant and tangent. So if I look at the power of tangent x, I see that it is odd. So I could use the first case that we had discussed. And if I look at the power of secant x, well, I see I have an even power of secant x. So I could also use the second approach that we had talked about, where I factor out a secant squared x. So here, either approach will yield the same answer in the end. So it's just a matter of personal preference which approach you prefer to use. So here, I think my preferred approach would be to factor out a secant x times tangent x. So if I factor out a secant x times tangent x from my integrand, I would be left with tangent squared x times secant x to the 5th, and then I have on the end the secant x times tangent x, which I had factored out. Now, after I factor out my secant x times tangent x, I want to rewrite everything else in terms of secant. So I'm going to use the fact that tangent squared x is equal to secant squared x minus 1. So I will have a secant squared x minus 1 times secant x to the 5th power times secant x tangent x dx. In grouping all of my secant x terms together by distributing the secant x to the 5th power, I have secant x to the 7th minus secant x to the 5th, all times secant x tangent x dx. Now from here, I'm going to make use of a substitution where u is chosen as secant x, so that du would be secant x times tangent x dx. So rewriting my integral in terms of u, I would have u to the 7th minus u to the 5th. And then on the end, the secant x tangent x dx, when we made our substitution, we found that was exactly equal to du. So after my substitution, I'm left with the polynomial in terms of u, and I can integrate directly, leaving me with a 1/8 u to the 8th minus 1/6 u to the 6th plus c, or taking u, which was secant x, and substituting in for this answer, we have a 1/8 secant x to the 8th power minus 1/6 secant x to the 6th power plus c. All right. Now, in a similar way, you could have factored out a secant squared x from the integrand in the beginning, because the power of secant x was even, and then you would be left with a secant x to the 4th power, and then you could use the fact that secant squared x is 1 plus tangent squared. But then what makes that a little more difficult is you would have something of the form 1 plus tangent x squared quantity squared, which you would have to expand. So your answer gets a little bit messier if you use that approach. However, using that approach would yield an answer that is equivalent to the one that we found here. So let's look at another one. In part D, we have the integral of tangent x squared. So here we don't have anything in terms of secant x. We only have an even power of tangent x. Now, if we only have an even power of tangent x, then we could use the third case that we had discussed for these trig integrals involving secant and tangent, which said that we could take our even powers of tangent, in this case tangent squared x, and make use of the identity that tangent squared x is equal to secant squared x minus 1. And let me check this briefly. Make sure I'm using the correct identity. Tangent squared is secant squared x minus 1. Yes, okay. So after I rewrite tangent squared x as secant squared x minus 1, I can integrate each of these terms directly. So let's think about this. The antiderivative of secant squared x is tangent x. Recall the derivative of tangent x is secant squared x. Therefore, the antiderivative of secant squared x is tangent x. And then we are subtracting the antiderivative of 1 dx, which would be 1x plus an arbitrary constant c. All right. So let's consider another example, working with that third case of powers of secant and tangent x. So in part E, we have the integral of secant x cubed dx. So we recognize this immediately as a trig integral. It's involving powers of secant and tangent x. And we have to consider which of the three cases we're working with. So first off, there is nothing involving tangent x. So certainly we're not working with the first case in which tangent of x was an odd power. Now our next case was if we have an even power of secant, which we can see that we do not here. We have an odd power of secant. So our third case is the case that we're working with, where we have only even powers of tangent and odd powers of secant. Now, in that case, we were supposed to take any even powers of tangent and rewrite them in terms of secant. However, we don't have any tangent terms here. So all that we're left with is this integral of secant x cubed. Now, in that third case, I claimed that we could use integration by parts to evaluate these odd powers of secant x. So let's see how we could do this. I'm going to try to make use of integration by parts, and in order to do this, it might be helpful to rewrite secant cubed x as secant x to the first times secant squared x dx. Now recall the method of integration by parts says that we're supposed to choose part of our integrand as u and part of it as dv. So here I'm going to choose u as secant x, in which case dv is secant squared x dx. Then it follows that du, the derivative of secant x, would be secant x tangent x, and then I'm multiplying by a differential dx. And v would be the integral of secant squared x, which is tangent x. So using the integration by parts formula, the integral of secant cubed x dx is given by u times v, which would be secant x tangent x, minus the integral of v du. So multiplying v times du, we would have a secant x times tangent squared x dx. All right. So in this, or after we've applied our integration by parts formula, we're left with a new integral that involves an even power of tangent and an odd power of secant, which is still an integral in that third case that we had discussed previously. So in that third case, we were told to rewrite tangent squared x. So this part of my integrand, which is tangent squared x, I'm supposed to rewrite this as secant squared x minus 1. And then I still have my dx on the end. So let's see what we've got. We have a secant x times tangent x minus the integral of distributing. We have a secant cubed x minus secant x dx. Or if I split this, I have secant x times tangent x minus, when I split this integral, I have the integral of secant cubed x dx minus the integral of secant x dx. And I was subtracting that quantity. So distributing the negative, I have secant x tangent x minus the integral of secant cubed x dx. And then minus the negative gives me a positive integral of secant x dx. So what I have now are two integrals. This integral on the end, we know how to evaluate. We've come up with the formula for the antiderivative of secant x. We had looked at that in section 1.5 on substitution. And this other integral that I have is the integral of secant cubed x. So you might recognize that immediately. Well, that's the same integral that we had started with. That is the integral on the left-hand side of our equation here. So let me copy that down below. We have the integral of secant cubed x dx is equal to the following expression. So I see this same integral appear on both sides of the equation. So I get something similar to a loop integral that we had considered when we talked about integration by parts. And in order to solve for this integral, I'm going to group these two terms together. So if I take this term, the negative integral of secant x cubed, and I add it to the left-hand side, I would then have 2 times the integral of secant x cubed dx is equal to, well, we would be left with a secant x times tangent x plus the integral of secant x dx. But I know how to integrate secant x dx. It's given by the natural log of the absolute value of secant x plus tangent x. And on this left-hand side, I still have twice the integral of my secant x cubed dx. So in my last step, in order to solve for this integral that I want, I need to get rid of the factor of 2 in front of it. So dividing both sides by 2, I find that the integral of secant x cubed dx is 1/2 of secant x times tangent x plus 1/2 of the natural log of absolute value secant x plus tangent x plus c. This was an indefinite integral, so at the end I can't forget to include my constant of integration. So this antiderivative of secant cubed x is a little bit difficult. We have to use integration by parts in order to evaluate this. And in general, if we were to consider higher powers of secant x, like secant x to the 5th, we could use a similar approach that would take a few more steps to complete. Now, it might seem at first like this sort of integral would never appear in applications, but we will see some examples later in this course, and you might see some, well, actually, I know you'll see some examples in your Calculus 3 course that will require you to integrate this secant cubed function. So it is a little bit tricky here.